Look at Hong Kong. Millions of moving parts. Elevators, water pumps, power grids, and traffic systems are operating simultaneously every single second of the day. Historically, keeping an eye on all this hardware required physical inspections. A technician had to drive to a remote facility, check the meters with a clipboard, and wait for something to break before fixing it. At a city-wide scale, this method is too slow and costs a fortune. Connecting these sensors to the internet seems like the logical next step, but 4G, 5G, and Wi-Fi all present the same problems. Wi-Fi has a terribly short range. Cellular networks consume massive amounts of battery power, and they force the government to rely entirely on private telecom providers for data flow. For critical public infrastructure and safety, relying on a third party is a vulnerability. The data requires absolute privacy. The network needs specific customization, and the government must maintain total control over the security architecture. To solve this, Hong Kong's Electrical and Mechanical Services Department built something bespoke. This is GWIN, the government-wide Internet of Things network. To optimize a modern metropolis, a government cannot simply rent its nervous system from a corporation. It must build its own private, invisible layer. The foundation of GWIN is a technology called LPWAN, or Low Power Wide Area Network, specifically operating on the LoRa protocol. LoRa provides three distinct advantages for urban infrastructure. First is its extreme range. A single sensor can transmit data up to 7 kilometers away, penetrating through thick concrete walls and outdoor environments alike. The second advantage is cost efficiency. Because these sensors run on batteries, they eliminate the need for engineers to install complex, expensive electrical wiring across thousands of remote locations. The third advantage is absolute network independence. Unlike commercial options, a LoRa network is privately owned and operated on a self-owned core server. This independent architecture guarantees resilience. When commercial cellular networks are jammed by marathon crowds or knocked offline by severe typhoons, the government's private data continues to flow. By combining a 7-kilometer range, multi-year battery life, and total independence from corporate telecoms, LoRa bypasses the usual bottlenecks of urban data collection. It clears the path for massive deployment. To test this at scale, the department rolled out a pilot program in Hong Kong's Sha Tin district, hitting an 80. They installed 34 dedicated gateways across public facilities, bolting them onto fire stations, municipal buildings, footbridges, and water reservoirs. The intelligence gathered is immediate and dense. This live dashboard from the Sha Tin deployment displays 491 active sensors, transmitting over 1 million messages from the field. Every single one of those data points routes directly from the scattered city gateways back to a centralized brain at EMSD headquarters. The Sha Tin experiment proves that a private, high-density sensor network is a live operational reality, harvesting unprecedented levels of environmental intelligence. But collecting millions of data points is only the first step. The goal is to translate that raw data into daily operational changes. It starts with the Internet of Alert thing. Instead of waiting for citizens to complain about a broken elevator or a malfunctioning filtration plant pump, remote sensors detect the fault and flag it instantly. The next level is the Internet of Control thing. Operators actively interface with remote hardware, adjusting the dimming on public lighting fixtures to maximize energy efficiency. They also continuously monitor the ambient temperature, humidity, and real-time electrical current flowing through critical equipment like heat pumps. Through these applications, the city's management model moves from a blind, reactive entity into an active, real-time controller of the physical environment. The highest evolutionary tier of the GWIN system integrates artificial intelligence. This allows for what is known as predictive maintenance. By feeding continuous sensor data into an AI model, the system analyzes microanomalies. If a motor's vibration pattern changes by even a fraction of a millimeter, the AI flags it, predicting a mechanical failure before the machine actually breaks down. The old run-to-failure model results in sudden breakdowns that cost significant time and money. An AI-predicted, scheduled intervention requires a fraction of the resources and keeps the system online. This transformation of Hong Kong's infrastructure, from Sha Tin's water reservoirs to the elevators in municipal buildings, is entirely enabled by this low-power, wide-area private network. By anticipating failure before it occurs, a smart city transforms chaotic crisis management into a system of quiet, invisible efficiency.